So this is exactly what I would like to talk to kind of argue that in life, when we talk with each other, when we discuss with each other, we learn new things, and everything in some sense it has to do with indistinguishability and how our perspectives evolve as we talk to each other. But of course, it's not just a philosophical talk. It will actually be a little introduction to this research area, which is very fascinating because it has discovered that distributed computing is very, very closely related to topology, actually. So let me just start by saying a few words about what is distributed computing, which is really, in some sense, the science of indistinguishability and perspectives, because in distributed computing, what we have is a system that is composed of many computers. Sometimes these computers, we call them agents, or sometimes we call them processes or processors, depending on the context. But the thing is that each one of these computers is talking to the other computers by some means. But actually, also the state of the distributed system consists of the state of many computers, maybe even the state of the communication channels. Actually, the computations that the computers do are just made based on their own local data. So, in some sense, what we have is that knowledge comes into play, because knowledge is about what we know locally about what the global situation is. Even from the beginning of the TARC famous conference on reasoning about knowledge that started in 1986 and has been going on since then, with applications to many areas like game theory and philosophy and logic and computation, Joe Halpern tells us the intuitive idea of knowledge is that besides the true states of affair, there are a number of other possible states of affair, or possible worlds, which is the way they are called. Different global situations are worlds. Some of these possible worlds may be indistinguishable to a specific agent from the actual true world in some sense. So here is just a little example of how we have two worlds: the situation, the global situation V, the global situation, the world W, and there is some computer, some agent that does not distinguish between the two global states, because its own local state is the same in both worlds. So we may draw it as a graph with the two worlds and an edge joining two worlds labeled with the agent that does not distinguish between the two worlds. And in distributed computing, we know for many years that actually indistinguishability is the source behind all of the limitations of what we can do in a system where many computers are collaborating with each other. There was a very important survey already in 1989. Already there was a survey describing hundreds of impossibility proofs for distributed computing by Nancy Lynch, and a few years Faith Ellen and Eric Rupert published another one of hundreds of impossibility results in 2003. And what they say here is exactly this quote: there is a fundamental idea underlying all of these hundreds of impossibility proofs of what are the limits of distributed computation, and they all come from limitation imposed by local knowledge, essentially indistinguishability. And let me give you a few examples of the wide variety of sources where indistinguishability comes from. Well, perhaps the most basic that we all know is real time, that is not observable, or one could say that it doesn't even exist according to relativity theory. So we cannot distinguish between when exactly a moment happened in some distributed system. Another is locality. By its very nature, the distributed system is spread geographically, sometimes even in the whole world, but even in our small multi-core systems that we have, even in our mobile phones, things are distributed. So information takes time to propagate from one computer to the other. And for some time, while this information is flowing, one computer cannot distinguish what is the state, the last state of another computer in this system. Many of these systems have different properties about timing, about the relative speed of the communication, of the processing. In some systems are completely asynchronous in the sense that one computer can run at one speed arbitrarily, maybe even changing its speed, while another computer is running at a completely different or related speed. But sometimes in many systems, the speeds of computation of the different computers are actually quite related, and we call them partially synchronous systems where the speeds cannot vary too much one with respect to the other, or the messages, the communications are also kind of somewhat bounded in time. But even in systems that are fully connected, there is a direct communication link between any two pairs of computers, and even if they run exactly at the same speed, in a synchronous way, still there is indistinguishability because of the possibility of one computer failing, and maybe this computer communicated with another computer, but the computer that receives information cannot distinguish whether another computer did not receive the information because there was a failure in between the two events. And I will give a few examples how right from the beginning of the computation there is indistinguishability, because the inputs, even at the beginning of the computation, every computer, every agent has some local initial state, which the computers may not know what are the inputs, or may not know everything about what are the inputs in other computers, so they cannot distinguish between two possible inputs in another computer. And there are many other indistinguishability sources that come from more technical aspects of the current technologies that we use, that it's not very relevant for this talk, but just like we mentioned, that even whatever the way the systems communicate with each other, for example, if they communicate by writing and reading a shared memory in a multi-core microprocessor, or sometimes in mobile robot agents, there are issues about the lack of knowing what is the name of other processes, or about symmetries, that they don't have the same orientation of the space where the robots are moving. There are many technical situations in many kind of different distributed systems that have been studied. So when things become even more interesting is when you analyze the combination of this indistinguishability and the local perspective that each one of the participants has in a given situation. And that's why I say that distributed computing is, of course, a matter of perspectives. And what it becomes really fascinating is what you analyze, how these perspectives evolve as the computation is moving and computers are communicating with each other, learning things about what the other computers know and the state of other computers, and then their perspective evolve and distinguishability relations also change. Let me give a little funny example about perspectives in real life of this experiment reported, for example, in The Economist a few years ago, where it is known in researchers in life sciences that those who study animal behavior have long feared that their mere presence might affect the outcome of their experiments. And in this situation reported in The Economist, it was noticed that when the mice had a female researcher in the room with them, the injections induced visible distress. But when the researcher were a male, the animal showed fewer signs of pain. So it's just a little funny example how in life and also in really distributed computing systems, perspectives are very complicated and evolve in very interesting situations. And this is actually what we discover in this area that is now more than 25 years old, where we actually have have noticed that actually, in some sense, distributed computing and topology are two sides of actually the same things, and I will try to explain a little bit more in this talk why they are the relation is so intimate. But also you can see the book where we collect many of these results with Maurice Herlihy and Dmitry Kozlov. So let me start with a few simple examples of how do you represent the structure of indistinguishability in a system using simplicial complexes. So suppose that you have three computers. I will call them Alice, Bob, and Kath, A, B, and C. And each one has its own local perspective of some global situation, the world. So in distributed computing, since the only thing that exists is actually the perspectives themselves, not the global states. Nobody sees the global states. Each participant only has its own perspective. Then what we have is really a set of three perspectives, and we draw it here as a triangle, as a simplex. The vertices of this triangle are the perspectives. We have one vertex for Alice, one vertex for Bob, and one vertex for Kath. And the vertices are labeled with a pair of values. One value is the name of the part of the computer, of the agent, and the other value is the view, the perspective that this agent has. Here's another example of another possible world. So in this other possible world, Alice, Bob, and Kath, have some other perspectives. But by chance, in this situation, notice that Alice and Bob actually have the same perspectives in both of these simplexes. So actually, these vertices are actually the same vertices. So what we have is that the two triangles share an edge, and we really get a simplicial complex. But semantically, it's very nice, because what we are seeing is that we have that the fact that the two simplexes share an edge means that both participants, Alice and Bob, cannot distinguish between the two situations, and only C, Kath, can distinguish between the two situations. So this directly leads us to combinatorial topology that studies space constructive or discrete pieces. And what I will like to show later on is how the topological invariants of under subdivisions actually come into play in these distributed computing situations. But I cannot help but remember this nice quote from the book of the classic book of Combinatorial Topology by Herlihy, where he says that in combinatorial topology, it is remarkable that the only machinery needed to make topological deductions is the elementary process of counting. This is the miracle of combinatorial topology. And when you think of it, the miracle is even more wonderful when you understand that this huge area, very, very deep area of algebraic topology, in the bottom is just this miracle of little counting arguments between different. So this is why also the connection to distributed computing is so fascinating. Anyway, let me start to give you a few more concrete examples of problems that appear actually in distributed computing research via the analogy to card games. And I will give you a few examples. The first example, we have our three agents, Alice, Bob, and Kath. And now there is a deck of three cards. The cards are called 0, 1, and 2. And simply each person draws a card from this packet of three cards. And only each person can only see his own card. So we can represent all possible ways of drawing cards in the traditional way instead of the simplicial complex way, which are called Kripke structures and are the basic of many things in epistemic logic and reasoning about knowledge. And this is the way they represent all the situations, because for them, they thought that the basic element is the world, the global state, and not the perspective. So we draw a vertex for each one of the possible perspectives of global states. So, for example, this vector represents the situation, the global world, where Alice draws card 0, Bob draws card 1, and Kath draws card 2. And of course, then we have each world is represented by one of the possible permutation of these cards, of dealing the cards. And the edges are labeled with the agent that cannot distinguish between two of these situations. For example, Alice, when Alice gets card 0, Alice cannot distinguish who got the other two cards, whether Bob got card 1 and C got card 2 on the left, or the other way around on the right side of the edge. And then we have a little graph that represents the indistinguishability structure at the beginning of this game when each one gets a card. But of course, in distributed computing, there are no global states. They are only the local perspective of the participant. So we, from the beginning, thought that it was more natural to consider the dual of that Kripke graph, which is the simplicial complex that I have just represented in this slide. For each vertex of the Kripke graph, now there is a triangle, a simplex, a two-dimensional simplex in the simplicial complex. This one, Alice gets 0, Bob gets 1, and Kath gets 2. And the way to draw the picture more compact and nicely, I draw each vertex with a different color. The color represents the name of the agent, and the value inside the vertex represents the perspective that this agent has. So in this triangle, the white vertex represents that Alice has card 0, the black vertex represents that Bob has card 1, and the gray vertex represents that there's Kath that has the card number 2. And you see that sometimes two vertices share an edge. Why? Because two triangles share a vertex because one participant doesn't distinguish. And notice also that this Alice, I duplicated the vertex of Alice when Alice gets card 0 just because it was easier to draw the picture, but you should pay attention that that vertex is actually the same vertex. So you can imagine this simplicial complex, how it would look in a three-dimensional space. What is nice now, what becomes really fascinating is what happens. How does this structure change? This simplicial complex changes as communication evolves. Let's see a little example where Alice suddenly announces, I do not have card 1, and everybody listens to this public announcement. Then they all realize that actually the white vertex where Alice has card 1 actually cannot exist. So they remove them from their mental picture of all the complex of all the possibilities, together with the two triangles, because now they are not possible. They just learned from listening to Alice that those two simplex are not possible. And then what happens? That Bob learned nothing, because the black vertices of Bob still belong to two triangles. Why? Because Bob is the one that has card 1, so of course Bob did not learn, but in the structure of the simplicial complex, how do we see that Bob did not learn anything? Because still every vertex of Bob still belongs to two triangles, so still Bob still has the same uncertainty, that the same indistinguishability relations with respect to Bob, but instead Kath, in this vertex that I am labeled, Kath now knows what exactly happened, because now the vertex of Kath labeled 2 now belongs to only one triangle, because indeed now Bob knows that there's only one possibility. If Alice does not have the card 1, it must be that Bob has the card 1 and Kath has the card 0, and this is how the indistinguishability is noticed actually in the simplicial complex, and knowledge is gained. So in some sense, knowledge is the dual of indistinguishability. Let me give you another example of a simplicial complexes that appear in distributed computing very commonly. Suppose that now we have our 3 participants, but now the deck of cards consists of 4 cards, 0, 1, 2, and 3. How does the simplicial complex look like? Actually, it looks like a torus. We have all the triangles. For example, this triangle represents, actually simply it represents that the 3 participants got 3 different names. And each edge belongs to 2 triangles, because once you fix the 2 cards that these 2 participants got, there still is uncertainty whether the card of the black vertex, namely of Bob, if Bob got card 1, or Bob could have gotten card 3. That means each time you see the cards of 2 participants, the third participant still could have gotten 2 possible cards. And if you draw the possibilities, you can see that this the simplicial complex that you get is a subdivided torus. And this actually appears in several important applications in distributed computing related to renaming, where the computers get some names initially, they need to talk to each other and decide on new names, which maybe come from a smaller space of names. Another kind of complexes that appear in distributed computing is what we call pseudospheres, because in many situations, the inputs, these cards that they can get, are completely independent from each other. So let's see a situation where Alice, Bob, and Kath now draw cards from a deck of 6 cards. 3 cards are identical, and they are called 0, and another 3 cards are also identical to each other, and they are called 1. And now Alice, Bob, and Kath draw 1 card of these, so now they can draw any combinations of 0s and 1s correspond to a possible initial state of the system, which you can see that it's actually a subdivided sphere. In this case, you have one triangle where the 3 participants get card 0, another triangle when the 3 participants get card 1, and all around you get all the combinations of 0s and 1s, so you can see why this is a subdivided triangle, but a subdivided sphere. And more generally, what we get is a wedge of spheres when you have even more participants and any number of cards. Now, for example, suppose you have these 4 cards. Another situation that appears in distributed computing is that they can draw cards from this deck of 4 cards in any way, except that you are sure that never it will be the case that all 3 participants will get the same card. So here is how it looks, the simplicial complex. You have all combinations actually of 0s and 1s, except for the triangle in the middle that is a hole. It doesn't appear there, where all 3 participants get 1, and the other triangle outside where all 3 participants get 0 is another interesting complex, and generalizations of this complex appears in distributed computing. So for example, in this edge, Bob and Kath, they know they do not know what is the card of Alice. It could have been 0 or it could have been 1. So this appears in a class of problems called weak symmetry breaking distributed computing. It looks like a subdivided cylinder, if you want. Okay. Let's analyze now. The interesting thing comes into real play when you see that actually when the participants talk to each other, the simplicial complex evolves and it preserves some topological properties. What this makes this area so important and the connection to topology so intimate is that how well the topology is preserved actually depends on the quality of the communication, of how reliable is the communication between the processes. Let's see an example how when the communication is very unreliable, then actually the topology is perfectly preserved. You obtain a subdivision of the initial simplicial complex. Suppose the three players that they got their cards now talk to each other, they tell to each other the cards by announcing publicly which one is the card that each participant got, but this communication is very unreliable. When a participant announces his card to the other participants, it could be that they miss the announcement, the other participants. So let's see how what we get is actually a subdivision of the initial simplicial complex. We have on the left the initial simplicial complex, where Alice, Bob, and Kath draw binary cards, except for the situation where they all get 1 and they all get 0. Then they make these public announcements, and all possibilities of who misses the announcement is possible. And let's analyze what happens. Suppose we analyze what happens with the triangle on the left, where 2 of the participants get card 0, the black one and the gray one, and the white participant gets card 1. And now they announce to each other their cards in this unreliable way. And now you have all these triangles, are all the possibilities. The triangle of the center represents the situation where they all listen to each other correctly. So now what is the perspective? The perspective changes. The initial perspective, the initial view of each participant was only its own card. That's why every vertex was labeled only with one value. But now, after communication, every vertex is now labeled with a vector of values, which represents its new knowledge about the situation. In the triangle on the center, they all learn to each other cards, so they all know the full vector of what was the initial draw of cards. But they are not sure if the other participants listened correctly. So, for example, I am here pointing on the simplicial complex on the right, these 2 arrows. One arrow represents the situation where the white vertex and the black vertex, they did hear correctly, but the gray vertex missed completely the announcement, and so he still, after communication, the gray vertex still only knows its own card. And then there is this other triangle on the bottom of the simplicial complex where actually there are 2 participants that fully miss the announcement. So the black vertex in the bottom triangle listens correctly to the announcements of the other participants, but the 2 participants in the bottom, the white one and the gray one, still only know their own initial draw of the cards. So you can see, if you analyze all the possibilities, that you get exactly a subdivided triangle, which will be substituted for the initial situation. And what is interesting is that with this very unreliable communication, the topology is perfectly preserved. Each initial triangle on the left, after communication, will be substituted by all the combinations of who listened to which announcement, and each initial triangle will be substituted, will be replaced by the subdivision on the right, and the full simplicial complex on the left will be replaced by a subdivided version of that initial situation. So the topology will be perfectly preserved, and this is a general theorem actually in distributed computing that we have, that when the communication is very, very unreliable, whatever the initial simplicial complex is, it will just be subdivided after communication happens. Actually, what is beautiful about this theory is that if the computers continue talking to each other and telling to each other what they know about each other, if the communication is very unreliable, the only effect will be to subdivide further and further the initial simplicial complex and have finer and finer subdivision. So it turns out that a whole branch of research in the connection between distributed computing and topology has to do with finding techniques to prove topological invariance about the initial simplicial complex and to find which are actually the topological invariants that are preserved, because which topological invariants are preserved depend on the exact model of communication and the exact model of failures about these different agents and participating in the distributed system. Let me give you a little example of this kind of techniques of how do you prove topological invariance about the initial simplicial complex, which is called the critical state argument, which is actually the oldest of these arguments, because it was discovered before the connection with topology was fully uncovered. At the beginning, only one-dimensional connectivity was understood that was playing a critical role, and later it was discovered that any dimensional connectivity was also playing a role in distributed computing. So suppose you have just two agents, P and Q. Now let's call the two agents, the two computers P and Q, and suppose they communicate by a very simple operation, which is writing and reading to a shared memory where they can deposit values. In this example, I'm representing by a vertex some initial global state of the system of two processes, which is called X. And suppose P is trying to write to this shared place, shared memory, something that P knows, and Q is trying to read what P wants to write. So in the program of P, the next operation is to write. In the program of Q, the next operation is to read in this global state X. And now, what happens? Actually, in this system, it is possible that either of the processes is faster than the other and executes its own operation faster before the other operation. So it is possible actually that first P writes and then Q reads, and you have this little path in this graph of executions, of the possible executions of this system. But also it is possible that actually Q reads first and then P writes, and you have the path of the interleaving of the execution represented by the path on the right. And what makes indistinguishability appears because you can see that actually the process P cannot tell which one of the two interleavings actually happened, because when P writes, simply P writes to the shared memory, and it cannot tell whether actually Q read its value or actually Q executed its read operation before P wrote. So the new global state X in red in this picture, actually P cannot distinguish which one of the two paths actually happened. So this is the basic to prove, for example, that in an unreliable system, one-dimensional connectivity is a topological invariant. That means that if these initial global states of the systems are one-dimensional connected, just like a graph connectivity, the final states of the computation, no matter what operations and what order are executed, if the communication is unreliable, the final states will also remain connected. So we will use this kind of simple version from topology of one-dimensional connectivity, that if you have a simplicial complex which is connected, which consists of two subcomplexes, each one of the subcomplexes is connected, and the intersection is non-empty, then this whole simplicial complex is also connected. Well, actually, as you well know, this lemma is generalized to any dimensional connectivity. And this is kind of theorems of nerve lemmas and other simplicial combinatorial topology tools that exist to prove connectivity. But I would like to emphasize more on distributed computing and how topology plays a role, because I'm sure you all know well these kind of things of combinatorial topology. So what is the argument when this critical state argument to prove a topological invariant? If we would like to prove that the final states, after communicating with each other, no matter how many times processes communicate, say these two processes, P and Q, communicate with each other in this unreliable way, I would like to prove that the final simplicial complex remains connected. I assume by contradiction that it is not connected. So that means that as the execution evolves, there is one last state. This is this critical state where the connectivity is broken. So we have any final state is just connected because any final state is just represented by a simplex. So any final state, like in this picture, consists just of an edge, the state of the black process, the state of the white process is connected because it's just one simplex. And we are assuming for contradiction that is not connected, so there will be this critical state where it stops being, it's the last connected state. So we have in the beginning is disconnected, the computation, at the end is connected, and there is one last moment in the computation that it becomes connected. We look at that state, then we look at this diamond of what are the possible of communication operation of Alice and of Bob, who writes and who reads. We know that one of them will have uncertainty, will not be able to distinguish, and then this critical state, which was the last state where the complex was disconnected, we see that it remains connected even after these two operations because there is one process, in this case the white process, that still cannot distinguish, and then and still the simplicial complex remains connected. Okay, anyway, this I just wanted to give just a little bit of flavor of one of the possible ways of proving topological invariance, but let me now get into computability, which is the very interesting situation where we see that the problems that are computable in a distributed system actually are a function of topological properties, which is in a very dramatic difference between sequential computing, traditional computation, which is sequential computing, Turing machines, and you have computability arguments and undecidability arguments, everything based on Turing machines. And we see that when we move to a situation where you have many Turing machines, many computers instead of just one, many state machines, actually computability doesn't depend on Turing computability, it depends on topological properties. So let me explain a little bit how this works. Suppose we have the following problem. So this is another very nice situation. Simplicial complexes are also used to specify distributed computing problems. So I will specify this problem, the following problem. First, to specify a problem, as usual in computer science, when we specify a problem, we specify it by a function. We have some input, then a function, and you have which represents the outputs of the computation. Here, the input is not just a single value. The possible inputs to the computation is a simplicial complex, as we just saw in this example. What is the input complex? What we call the input complex for two processes, Alice and Bob, is a graph. If there would be three processes, you would have a simplicial complex, a two-dimensional simplicial complex. If you would have three processes, you would have a three-dimensional simplicial complex, and so on. So in this, to illustrate the ideas, we have only Alice and Bob, and they draw cards from this deck of 6 possible cards. 2 zeros, 2 ones, and 2 twos. And so here are all the possible ways in which they can draw, Alice and Bob can draw cards. Either both of them can draw card 0. So we have Alice, we have one of the participants is represented by the black color, the other participant by the white color. And in the center of the vertex, I am putting the name of the card that it got, this participant. So you have 3 vertical edges in this simplicial complex that represent the case where they draw the same card, both participants. And then you have the other edges of this graph, which represent situations where they draw different cards. And this is the input complex to some problem, some distributed problem that I am going to define now. To define the distributed problem, now I have to produce an output complex, which now represents the decisions, the computations that have to be made. That means that after they talk to each other, Alice and Bob can communicate with each other as much as they want, but eventually each one has to produce a decision value, which is the product of the computation, but it's a local decision value. And in this particular example of a distributed task, I would like them to have binary decisions. They talk to each other, and at the end of the computation, either both produce output 0, is the top edge of the simplicial output simplicial complex, or maybe they both decide 1, which is the bottom edge of this simplicial complex, or maybe they decide different values. One decides 0 and the other decides 1. To finish defining this distributed problem, I need to define an input-output relation, which specifies in each possible input simplex, after they talk to each other, what are the legal decision values that the two agents should decide. And this is what is called the Equality Negation Task, actually in a paper in the SciAm Journal of Computer on 2000 by Wei Kao and Vasos Hatzilakos, which is called equality negation because it is defined by this relation. If processes start with the same inputs, then naturally they should define different outputs. In contrast, if they start with different inputs, now they should agree on the same decisions. So I would like, for example, on the top edges, if they start, for example, in the edge on top where the black vertex starts with input 0 and the white vertex starts with input 1, they should talk to each other and they should actually agree on on either both should decide 0 or both should decide 1. Similarly, in the next edge on the top, if the white vertex starts with input 1 and the black vertex starts with input 2, they have to talk to each other and they should both agree either on the edge 0, 0 or on the edge 1, 1. Each one should decide, both of them locally, each one should decide 0, or both of them locally, each one should decide 1. And I would like to explain why topological arguments actually show that this problem has no solution if the communication is very unreliable by talking to each other in simple way, by just maybe reading and writing or sending messages to each other with their values. And the reason is because of this topological connectivity invariant that no matter how much they will talk, actually the only thing that they will do to the initial simplicial complex is to subdivide it farther and farther and farther. So let's see what happens. We look again at the two edges at the top of the input simplicial complex. And if you believe me that no matter how much they talk to each other, if the communication is unreliable, the only thing that the communication will be doing is to subdivide these edges. They may talk more and more and more. The only thing that they will do is to subdivide in a finer and finer way each of the edges. But in the end, they have to stop. Once they stop, they have to produce an output. So the computation, what it's doing is subdividing farther and farther and farther. For example, if we look at this at this edge, for example, and then at the next edge, they talk to each other, eventually they stop, and you get a subdivision of the two edges. And now they have to make a decision. A decision is local. So a decision is actually mapping each of the vertices of the subdivision to either both zeros or both ones. Suppose, without loss of generality, that they both decide zero. Since the inputs are different, they must decide either both zero and both one. Let's suppose that they decide one. So actually, these decisions, what they are doing is actually building a simplicial map, because each vertex in the subdivision corresponds to a local perspective of one of the processes. It makes a decision, so it's mapping each one of the vertices of the subdivision to each one of the vertices of the output complex, which correspond to the actual decision made. So actually, what producing decisions based on a simplicial complex actually topologically is represented by a simplicial map into the output complex. Since simplicial maps preserve connectivity, no matter how much you subdivide these two edges, by the simplicial map, they will just continuously be mapped into the edge on the top. Back and forth many times. How many times? As much depends on how much they talk to each other and how fine the subdivision is here. But anyway, all of these edges will be mapped into the edge at the top without loss of generality. Let's analyze now this edge. When black starts with card 0, white starts with card 1. Now they talk to each other many times. They subdivide this edge many times with all the possible perspective of who missed the announcement and who didn't miss not the announcement. Eventually they make a decision. This decision for each subdivided edge there will be mapped to this one, because if they both start with the same input, they have to design the same output, so it will have to go here. And now we see what will happen to this edge. This edge represents the situation where one starts with 0 and the other starts with 2. They talk to each other many times, they subdivide it, and then they have to decide. But where is this edge going to be mapped? This edge will somehow have to jump from the vertex in the output complex 1 to the vertex of the output complex 1. So somehow this edge, when it is mapped under the simplicial decision map, it will somehow have to cross the edge 0, 1, and the correct specification of the task will be violated, because an edge with different input values will have to still go through an output edge with different values, which is not possible. And an edge with different input values should always go to edges, should always be mapped on this decision map to edges with the same output values. So this is a little example how a topological invariant induced by the communication model actually is defining whether a decision, a distributed problem is solvable or it's not solvable. And this kind of problem, and in general, this situation generalized to higher dimensional connectivity and determine, and you can show that the computability of the distributed problem really depends on topological invariance. So to conclude, indistinguishability plus perspective gives us distributed computing via combinatorial topology. Simplicial complexes are used to model initial states and therefore initial states of computation in some distributed problem. Task specifications are input-output relations between simplicial complexes, which can be represented by some form of carrier maps, actually. Complexes evolve with communication and preserve topological properties, which depend on the specific reliability of the distributed system, the type of failures, the type of asynchrony, the uncertainty about what is happening in different parts of the system. And computability, whether a distributed computability actually depends on the existence of simplicial map between the two complexes. These simplicial maps are not arbitrary. They have to respect the distributed input-output relation on which we are interested. So this is a very small introduction to this area, just to finish with a philosophical complex. In reality, this is what we have. We have only local perspective. There is no global truth. Simply each participant has its own version of what is the truth. And perspectives are all sides of the same coin. But which coin? There is no coin. There is no global truth. There is no global world. There are only perspectives, which is what determines what we can do in distributed computing and in any distributed system, such as the one that we belong as human beings, which we all have our own local truth, our own perspective. We talk to each other. And so, therefore, in some way, when we talk to each other, when we communicate, what we are really doing at the bottom is some topological properties of subdividing and preserving some of the topological properties of the initial possible views. Just to finish with this little example that of which there are many in movies, in books, of how a story can be told through the eyes of three different participants in the system in a very, very different way. So, thanks for your attention.